today is, of course, Dror, and he will be giving us homework. But before I let him speak, I have talked to the person who knows things and about the Thursday night. So the hotel can feed us as late as 8, but to be able to do all the sledding and come back for 8, we need to leave here about 6. So what we were thinking is to move Pavel's talk to 3:30, so we would have 2 talks starting at 3:30, so slightly shorter lunch break. And then we have afternoon tea, so you can have a quick cup of hot tea before we go sledding, and then go sledding. Are we still in support? Hands up if you're still in support. Okay, so we'll talk to the hotel then and make the change to the schedule. We'll have a slightly shorter lunch break on Thursday and then go sledding after. And doors up.
Yes, so Zuzi failed to tell you how much I prefer color and sparkle over substance. So when I go into a donut shop, I will always pick the one with the colorful, sparkling things and not the one with the good ingredients. You know, I tend to have sparkles on my nails and dress in color and have colorful handouts. And the other thing that, oh, hello, Anton. The other thing is that, you know, often a birthday conference is sort of a burial ceremony. And that's why I'm speaking. I want to emphasize that you'll have to suffer through my colorful and sparkling stuff for a few more years. Okay. Anyway, so I'm going to start with a quick review of a recent paper with Roland van der Veen, fast, strong, topologically meaningful, and fun knot invariant, and colorful and sparkling. And then I'm going to assign homework, so I'm going to quickly go down the list of 27 homework assignments, and hopefully I will be done even ahead of time. Oops, I forgot to start my timer. Okay. So my talk follows the handout. I hope you're all holding a copy. And also it follows a paper. And here are the first 3 pages of the paper. And here are the remaining 32. And obviously you cannot read it, but the point is you get a general impression. And in fact, with good enough magnifying glasses, you should be able to read it as well. But the impression should be, yeah, color and sparkle over substance. Anyway, so again, I am going to give you a brief review of the invariant and then tell you why it's fast, strong, topologically meaningful, and fun, and then assign homework questions. So let's start with the definition. So part A of the definition. So with T a variable, we start from a matrix A, which happens to be a presentation matrix for the Alexander module of the knot K, coming from the Wirtinger presentation, but I'll just define it, just so that you'll have a general impression of what it looks like. So basically, A is the 2n plus 1 by 2n plus 1 identity matrix. If a knot has n crossings, and you cut it open, then it's going to have 2n plus 1 edges, 1, 2, 3, 4, 5, 6, 7 in this case. So you start with the 2n plus 1 identity matrix, and you add to it a contribution A sub c, one such contribution for each crossing. And basically, each crossing is characterized by a sign that could be either +1 or -1, and by 2 indices, namely the index of the incoming upper edge and the index of the incoming lower edge. I call them I and J. And the contribution A sub c will be in row I and row J, and in column I plus 1 and column J plus 1, you'll insert a block like this. So basically, the yellow crossing has I equals to 3 and J equals to 6. And therefore, in row 3 and row 6 and column 4 and column 7 of the matrix, you'll be inserting a copy of this block. That's the end of part A of the definition. Next comes part G of the definition. So you let G, which is a matrix, and the entries are called G alpha beta, and sometimes I call G alpha beta the two-point function or the green function or the traffic function, be A inverse. That's all. So you invert the matrix from the previous part, you get this horrible thing, and then and by the way, the previous part kind of made sense topologically. It's a presentation matrix of the Alexander module. Inverting a presentation matrix doesn't make sense. So hence that character here is making a horrified face. I should say that this matrix also has an interpretation which I will not review, but it has an interpretation as traffic function. So you can design rules for how traffic travels or not, and then G alpha beta is the amount of traffic that you read in position beta if you inject a constant flow of traffic in position alpha, and if traffic drives according to these rules. Anyway, then you let T1 and T2 be new indeterminants, new variable. You let T3 be the product of these, and you let G nu, where nu is equal to 1, 2, or 3, be, or you also call it G nu alpha beta, be G with the substitution T goes to T nu, where nu is 1, 2, 3. So you now have three matrices that look more or less like this one. And then comes part theta of the definition. So you define an invariant lowercase theta to be some normalization, delta 1, delta 2, delta 3. Oh, did I say it? Delta is the determinant of this matrix, and it's the classical Alexander polynomial. So you let theta be some normalization multiplied by a contribution that looks like the theta graph. So let me explain it. It's a double summation over the knot. So you sum over pairs of crossings, C0 and C1. And for each crossing, you take the product of three G functions, of three traffic functions or green functions or two-point functions. Basically things like G1 I0 I1, G2 I0 I1, G3 I1 I0, which mean like you count how much traffic there is starting at I0, which is the index of one of the edges near the crossing C0, and how much traffic goes from here to I1, which is one of the edges around C1, and then you multiply it, oh sorry, this is with the variable T1, and then you multiply it with a similar quantity with the variable T2, and then multiply it with a similar quantity of the traffic going backwards with the variable C3. And this is a schematic because there are actually several further contributions like that, because really you have to start in one of the edges near C0 and you end in one of the edges near C1. So there are actually quite a few choices, and the precise formula is a bit more complicated. You'll see it in a moment. Anyway, this gives you a polynomial in two variables, T1 and T2, sorry, Laurent polynomial in two variables, T1 and T2. And along with the Alexander polynomial, you get uppercase theta. I mean, the Alexander polynomial is a part of the computation, so you may as well save it. So you get a pair uppercase theta, which is a pair of a one variable Laurent polynomial, comma, a two variable Laurent polynomial. And then the next thing I want to say is, so actually this is theta. This is the invariant I want to talk about. And you know, if this wasn't a homework session where I assign homework, I would go through the proof of why it is invariant. But, well, no, I chose to assign homework instead. So I will not go through the proof. Okay? But I do want to go through like how do you present the data. So if you have a polynomial in one variable, Laurent polynomial in one variable, you can present it as a series of colors. So basically, wait, did I zoom in? Yeah. So basically, here is the polynomial 2 over t minus 1 plus 3t, and I represent it, yes?
So it was G1, G2, T3, so I thought it's T1, T2, T3 variables.
But T3 is T1 times T2.
Okay, thank you.
So it's only
And
two
T,
variables
and
at
T.
the end. What?
And T alone staying, who is this?
T alone is just for the Alexander polynomial. Okay? So inside lowercase theta, T alone disappears because all the things that appear are already after the substitution. T goes to T nu. Okay? So again, if you have a Laurent polynomial in one variable, basically it's a series of coefficients, and you can represent the series of coefficients as a series of colors. So red for positive coefficients, blue for negative coefficients, and the darker the color, the bigger the coefficient. Okay? So here is the polynomial 2 over t minus 1 plus 3t. Likewise, if you have a Laurent polynomial in two variables, you can present it as a two-dimensional array of coefficients and replace it by a two-dimensional array of pixels, namely a QR code or a picture. And so here is the polynomial t2 minus t1 times t2. So this is in pinkish because it's a positive coefficient, minus t1 t2. So this is in bluish because it's negative coefficient. And you know, this is positive powers of T2, this is positive powers of T1, this is negative powers of T1, and going down it's negative powers of T2. Okay? And then seeing that our invariant has a certain symmetry, it actually makes sense to change the coordinate system, and instead of using a rectangular coordinate system, you rotate one of the axes to make it a coordinate system like that. And what it does is it changes elongated hexagons into perfect hexagons. And then it also makes sense to draw the pixels as little hexagons instead of little squares. And so the exact same data that's here becomes this hexagon over here. So basically, the direction where T1 increases is this direction, and the direction where T2, where the power of T2 increases, is this direction. Okay? And, okay, so I finished the definition of the invariant, but now I have to tell you that it's fast, strong, topologically meaningful, and fun. So first of all, fast. So here is the full program that computes it. You're not meant to read it in detail, you're just meant to more or less see what it is, but basically this is the bulk of the program, and it's fun and nice, and basically if you look at it carefully, you see that this is the part where you make the matrix A. So A is the identity matrix, and you add to it for each crossing a block that looks like the block that I've shown before. Then delta is the determinant of A, G is the inverse of A, and then you add terms corresponding to this double sum over the knot. So that's the fun part of the program, but there is also the ouch part of the program, which is above it, and this is, so you see, as I mentioned, the theta graph contribution actually has many terms with each one with its own coefficient. And here is what they are. Okay, so it's a bit of a mess. but it's a mess that computers don't care about. So there are 18 terms here or something like that. But again, for computers, 18 is a small number. So in fact, for a computer, computing this invariant is very, very easy. Creating the matrix A is nothing at all. Inverting it, so inverting a matrix is something that computers know how to do relatively quickly. It's polynomial time, if you wish. And after that, it's a double sum over the knot. And a double sum over the knot is, much less than things like the Jones polynomial that involves an exponential amount of computation. Okay? And indeed, so here is the invariant of a random 300 crossing knot that we picked from somewhere. So the top is the Alexander polynomial. It's a barcode. It's not very interesting. And this is the hexagonal QR code. And I think that's the beginning of the assertion that this is fun. Okay? Okay, the next assertion is that it's a strong invariant. So again, I'm not going to go through it in great detail. I'll just tell you what is shown here. So there are 249 prime knots with up to 10 crossings, 801 prime knots with up to 11 crossings, and I've gone up to 15. So 313,230 knots with prime knots with up to 15 crossings. And then we're comparing the separation powers of various standard invariants and their combinations. So the Alexander polynomial attains less than 249 values. I think 211 distinct values on those 249 knots. So there is a deficit of 38. The bigger the deficit, the worse the invariant. So the deficit for 15 crossings is 236,000. So the Alexander polynomial is mostly deficit at that level. Okay? And here is a bunch of other invariants: the Levin-Tristram signature, the Jones polynomial, Khovanov homology, the Homfli polynomial, the hyperbolic volume, and then various combinations of them. And the deficit goes smaller and smaller and smaller as you combine more and more of those invariants until it gets to 40,000 and something. And then comes theta, and the deficit drops down to 6,700. And then if you add to theta all the other invariants, the deficit hardly drops anymore. So that's the case for it's a strong invariant. And here's another case. So all of those other relatively easily computable invariants do not detect knot mutation, but theta does. So here is theta on the Conway knot, and here is theta on the Kinoshita-Terasaka knot, and they're obviously different. And then came Zen's the topological meaningful. So theta is near delta. It has more or less the same ingredients as the Alexander polynomial, and the dream is that anything that the Alexander polynomial can do, theta can do too, maybe better. So in particular, here are two conjectures that, well, strictly speaking, they are conjectures, though I think conjecture one is nearly proven. But anyway, here are two conjectures that have analogs that are analogs of theorems for the Alexander polynomial. So the Alexander polynomial has some special property so it provides a lower bound for the genus of the knot, and the conjecture, which I think now is essentially a theorem. So the conjecture is that theta also gives a lower bound for the genus of the knot, and also if you have a fibered knot, then the Alexander polynomial has a special shape, and there is a similar conjecture about the shape of theta of fibered knots. And both of these conjectures were tested extensively, and the match is perfect. So basically, I think there's very little doubt that they're actually true. Okay? And then there is a dream. So the Alexander polynomial also has a special property on ribbon knots. in fact, on slice knots. So it's the so-called Fox-Milnor theorem or condition. And the dream is that theta has something to say about ribbon knots as well, but that's still a dream. And then my last thing to say about theta, before I start with homework, is that it's fun. So, you know, here's one case. Here's theta on the Rolfson table. It's clearly sparkly and colorful. What else? Of course it's fun. But more seriously, if you look at it, you'll see patterns. And you may, you know, want to go home and try to prove these patterns. Then here is theta on random knots with up to 50 crossings. Sorry, with 51 to 75 crossings. I'll say a little bit more about it later. But notice the patterns here. Okay? Here is theta on the 241 minus 41 pretzel knot. Here is theta on the 132 crossing torus knot, the 22/7 crossing knot. Again, I only am trying to tell you that it's fun, that's all. And there is a moral, and the moral is, well, if something is fast, strong, topologically meaningful, and fun, we must figure out all that we don't yet know about theta. Okay? So that's the end of my first 25 minutes or so. With a moral, okay? Now comes the homework assignments, the homework questions. So task number 1, make the data formulas human-friendly. I already told you that computers don't care that they're ugly, but we are mostly human, so no, I think we're all human. So we care. So can you make the data formulas more human-friendly? Task number 2. Sorry, I'm going to give you 27 homework assignments. It has to be quick. So task number 2. Prove the hexagonal symmetry of theta. So you saw it always had a hexagonal symmetry, and also I didn't show it, but it also has a certain behavior under mirror images and reversal of knots, reversals and mirror images, and but that's unproven. And in fact, it's less trivial than you may think, because even for the Alexander polynomial, so the Alexander polynomial is palindromic. So the Alexander polynomial, well, the barcode is palindromic, or the Alexander of T inverse is equal to the Alexander of T. And that was a conjecture for a few years in the early history of the Alexander polynomial. Yes, Dylan?
I mean, it sounds like just permuting T1, T2, T3 seems like it should be clear.
But it isn't. Because the data formulas are not symmetric under permuting T1 and T2 and T3. Okay? But even the Alexander polynomial, like it took a few years to prove the palindromic property, and the proof was non-trivial, and the really kind of good proof was once the Wirtinger presentation got thrown out and got replaced by Seifert surfaces. And only then the invariance under T goes to T inverse became clear. So we are still in the few years corresponding to the early few years of the Alexander polynomial. Task 2 pushes us beyond that. Task 3, so there is a similar invariant that I used to talk about previously, including even in Geneva. And it's the Rozansky over Bay invariant, which is only a one variable invariant. And the assertion is that it's the value of theta as T1 is equal to T and T2 is equal to 1. It's still not proven, but I think it should not be too hard. Task 4, homework assignment number 4. So, you know, is theta, oh, that should have been backslash theta, sorry about that. So, is backslash theta related to the invariant studied by Garoufalidis, Kashayev, and Lee? And I don't have a lot to say, except that they have a similar genus bound and a similar hexagonal symmetry, but they do seem to be different. So are they related? I don't know. Task task number 5, oh, so that's a fun one. So you know this thing about you put sand on a plate and then you play music to the plate and the sand bounces and then lands in certain shapes. These shapes seem to be at least reminiscent of the shapes that you see on the hexagons that present theta. So the question is why? Okay, and the reasonable answer is that there must be some dominant modes that that somehow in the, like when you evaluate the coefficients of theta, some contributions must be dominant and they must be somehow be related to harmonics or something. But that's in the space of coefficients, right? So what is it? Well, explain. I don't know, I shouldn't be saying this. I mean, this is your homework, not mine. Task 6. So prove the genus bound of conjecture 1. And there is actually a sketch of a proof here. And it says it's probably coming, and I think it's more or less there. So maybe I will not say too much. Yeah, maybe I'll skip the details. Okay? Task 7. So the G alpha betas were defined completely algebraically, but they are half invariant. So basically, let me explain. So if you have a knot, Christine, are you here? Hello, Christine. So if you have a knot, here is a knot. So you compute the G alpha beta, the amount of traffic from alpha to beta. It turns out that it's an invariant away from alpha and beta. So we call it a relative invariant, but what it means is that if you move the knot but away from alpha and beta, it's invariant. So you know, yes. So it calls for. So what is it topologically? What does it mean to be an invariant away from 2 points, and which invariant is it? And the best guess is that it's somehow related to equivariant linking numbers. And Christine knows about it more than me, so that's why I mentioned her. But I don't know. I don't know how to make it precise. Task 8. Ooh, that's a fun one, and I'm really sorry that Alberto Cataneo isn't here. So you see, since theta gives a genus bound, you'd expect that there is a formula for theta in terms, or the easiest way to explain it is if there was a formula for theta in terms of a ciphered surface. So the question is, find that formula. And the expectation, so assuming task 14, which I will mention later, we know that theta depends only of lower degree finite type invariance of sigma. So there is clearly a relationship with finite type invariance. And then the expectation is that there should be a formula for theta which resembles formulas for the Kontsevich integral. So the Kontsevich integrals has formulas where you count cosmic coincidences with signs. So basically, you count configurations where, so you have a certain number of pre-chosen points in S2, also known as stars in heaven, and then you count configurations in which you place a chopstick on the knot, and another chopstick on the knot, and another chopstick on the knot, and the chopsticks are all pointing at the stars in heaven, and you count configurations in which the chopsticks make a little tent or whatever. meet at some point in R3. So there are formulas for the Kontsievich integral of that form. And then similarly, there are invariants related to two-dimensional surfaces in R4 related to BF theory, and this is where Cataneo and Rossi play a role, and they're of the form. So you see here the two-dimensional surface is presented. Well, it's the green surface here. You can see it's a surface. It kinks around a bit just to emphasize that it's not necessarily a plane. And then you count configurations in which you have chopsticks in going into points in R4, but also chopsticks that lie on the surface of the knot. So I would expect similar formulas for theta using configuration spaces of points on the Seifert surface and outside of the Seifert surface. But I don't know them, so that's your homework. Sorry if, okay. Task 9, so you see that suggests that actually raises a point, like we don't know finite type invariants of surfaces. So you could say every finite type invariant, every Seifert surface is a thickening of a knotted graph. So the knotted graph here is in brown, and the thickening is in black, and it's a surface. So you can say let's try to understand finite type invariants of surfaces, but by first understanding finite type invariants of knotted graphs, but that's not intrinsic. That's making a choice. That ruins the symmetry. That's ugly. So is there an intrinsic theory of finite type invariants of surfaces? And furthermore, is its associated graded related to functions on H1 of the surface, which you would expect, but, well, I don't know it. Okay, task 10. So again, I'll go through it quickly. The point basically is that, so I want you to prove the fibered condition of conjecture 2. And in the case of the Alexander polynomial, the fibered condition is proven from the fact that, well, the knot complement, if the knot is fibered, is the mapping cylinder of a map from the Seifert surface to itself, and that allows you to write a presentation of the Alexander module of a very specific kind. And then you look at the order of that module, so the determinant of the presentation, and since the presentation was of a specific kind, it's written here, the order of the module, so the determinant of the presentation matrix, has a specific shape, and that's the property for the Alexander polynomial. So you would you would expect that proving the fibered condition for theta would involve finding a formula for theta, assuming that the Alexander module, or starting from a presentation of the Alexander module, which starts from a mapping cylinder of a map from the surface to itself. Well, it's your task, not mine. But you see, that suggests something more general. So maybe there is a formula for theta corresponding to each known presentation of the Alexander module. And there are plenty of known presentations for the Alexander module, and basically I want a formula for each one. So the Wirtinger presentation, which gives us the formula we have, is a presentation in which the generators are the edges of the knot, And there are two relations for each crossing. One is trivial, the edge before is equal to the edge after, and the other is a bit more complicated. Likewise, there is a then presentation in which the generators are faces and the relations come from crossings. Likewise, there is a co-then presentation, which is not terribly well known, but in which the generators come from crossings and the relations come from faces. There is the Bureau presentation, in which the relations come from braid strands and the generators come from braid strands. Then there is the Seifert presentation, in which basically you use H1 of a Seifert surface. There is also something with grid diagrams and which may be related to Higard-Floor homology. And there may be more. So basically, I want a formula for theta for each of these presentations. And, well, again, it's your homework. You already hate me? I'm sorry if I don't know. Maybe I'm 60, but I know nothing. Here are 27 things, 28 things that I don't know. So, okay. So there is a fun other formula for theta, which is actually the formula that I've already shown you, but written in a different way. So basically, it's a formula where you integrate theta, where you integrate the exponential of some Lagrangian, where the Lagrangian, well, it's written as a product over crossings of a local contribution for each crossing, but that's the same as saying that it's the exponential of a sum of contributions where you have a local contribution for each crossing, and you integrate it over a certain space which is a product over the edges of 6 variables per edge. And then there are some normalization factors and I don't know what. And the point is that this is a Gaussian integral, and so it can be computed using techniques from, essentially from quantum field theory, so Feynman diagrams and the like. And so I don't really want this integral to even be, I don't care if it's convergent or not, I define it using Feynman diagrams. And the claim is that there is such a formula for theta, and here is the Lagrangian. Okay? And in fact, when Roland and I found theta, we first found this Lagrangian, and the way we found it was we guessed that there is a formula of this general form because of other reasons, which actually I will come to later. And then, but it was too hard to figure out the coefficients, so we basically used the method of undetermined coefficients. We put variables for the coefficients and figured out which ones work. Okay? So the task is to write up the integration story, and in some sense it's a task for us. But you know, because we sort of know it already. But I'm really hoping that we will be spared. Okay, task 13. So there should be a similar Gaussian integral formula for theta, but instead of over 6 variables per edge, it should be 6 variables in H1 of a Seifert surface of the knot. And the quadratic part should be the same as in the Seifert-Alexander formula, but repeated 3 times. So the Seifert linking matrix, basically. And then there should be a perturbation that can be written in terms of low-degree finite type invariants of curves on sigma. There should be such a formula. Well, this really is a genuine homework assignment. Find it. Next, so theta is almost certainly, well, no, I would say certainly, the evidence is extremely strong that it's equal to the so-called two-loop contribution to the Kontsevich integral, though we don't know how to prove it. So in just a few words, the Kontsevich integral is valued in diagrams, and if you restrict your attention to two loops, then the main diagram is a theta graph with hair, and the hair gives you the variables t1 and t2, and so if you restrict your attention to two loops, you get a two-variable polynomial. And the claim is that, or more precisely, you get something messy, but you can extract the two-variable polynomial out of it. And Tomotada Ohtsuki studied this extensively, and almost certainly the two-loop contribution is theta. But we actually, strictly speaking, we don't know it. Yes, Dylan?
Would this answer task 2?
Yes.
Okay. All the symmetries.
Yes.
Okay.
Next. So there is another abstract place where theta is coming from. And again, I only have time for a sketch. So basically, if you have, let's say GLN. So, but here it's written for arbitrary Lie algebras. So GLN is more or less the sum of the upper triangular matrices with the lower triangular matrices. And in fact, the lower triangular matrices are the dual of the upper, via the killing form, of the upper triangular matrices. So all the information of GLN is in the upper triangular matrices. So the upper triangular matrices have a bracket, but they also have, well, their dual, which is the lower triangular matrices, also have a bracket. So the upper triangular matrices also have a co-bracket. And from the bracket and the co-bracket taken together, you can recover GLN. And this is the so-called Drinfeld double construction. So any Lie algebra with an extra copy of the Cartan is the double of the upper Borel subalgebra with its bracket and its co-bracket. And then you can do something funny and replace the co-bracket with epsilon times the co-bracket. And it turns out that if you mod out by some power of epsilon, such as epsilon squared or epsilon cubed, then what you're left with is a solvable algebra. And you can take solvables, I mean, there is a formal definition of solvable, but there is also an informal. Solvable means you can solve it. So basically you can write formulas for anything you do with the double with epsilon replaced by, with the co-bracket multiplied by epsilon. So you can write formulas for anything you do with such an algebra completely explicitly. And in fact, that's where we came from. That's where we started. So the invariant we get is most likely the invariant corresponding to SL3 to modulo epsilon squared. Well, complete this story and write it up. And again, maybe it's a task for us, but there's too much. So if we could help, it would be great. Yes, Dylan?
Did this also answer task 2?
No. Not obviously, at least.
So,
yes?
you expect this to explain the
Sorry?
You expect this to explain the hexagon symmetries that we...
That's the same question as Dylan.
Okay,
no, I don't expect it to answer the... Yes, Eva?
Sorry, more naive question, but does this provide some intuition or motivation for why I get the two variables, T1, T2?
Yes. Okay. And then there is task 16, So go beyond SL3 and the first power of epsilon, but I have to warn you that there are diminishing returns. So you can go to more and more complicated algebra and higher powers of epsilon. It's not done, but you can do it. It will be wonderful. I can imagine beautiful, very strong papers about it. But in fact, you'll be getting the polynomial time compute, the power of the polynomial in the polynomial time computability will grow bigger and bigger. Instead of a double sum over the knot, you'll have to be looking at triple sums, quadruple sums, and your computations will go slower and slower. So that's actually lower priority than first fully understanding theta. Task 17, you know what, how much time do I have? I'm kind of out of time, am I?
You still have about 5 minutes.
I have about 5 minutes. So, well, maybe I'll skip it, but there should be also a characterization of theta. Rather than a definition, there should be, it's the invariant with certain, which is in the kernel of something. That's what it means to have a characterization, I suppose. I mean, to have a construction, it's to be in the image of something, but I also want you to say it's in the kernel of something. So the Alexander polynomial is the simplest characterization is to extend knots to virtual knots and say the Alexander, or W knots, and then say the Alexander polynomial is really the kernel of the overcrossings commute relation, or it's the most general invariant that satisfies the overcrossing commute relation. And there ought to be a similar characterization for theta, but I don't know it, and I also don't even know how to spell characterize. I should also say that this G epsilon story should have an abstraction, a diagrammatic abstraction in the same way that the diagrammatic of the Kontsievich integral is an abstraction of Lie algebras. And now I'm talking to Pavel and to Benjamin more than to anyone else. So the Kontsievich integral is an invariant of virtual knots with values in a certain algebra of core diagrams, and then if you pick a specific Lie algebra, you can specialize to that Lie algebra and get values in some universal enveloping algebra related to that algebra, starting from your Lie algebra. But ordinary knots map into virtual knots, and more precisely, you should be thinking about rotational virtual knots. And similarly, there is a corresponding diagrammatic space, and instead of just having core diagrams or unitravalent diagrams or Jacobi diagrams, depending how you want to call them, you have arrow diagrams or diagrams with arrows in them. And then basically the arrow allows you to separate the upper Borel from the lower Borel, and so you more clearly get so you get something in the universal enveloping algebra of G epsilon. And it makes sense to mod out by powers of epsilon already at that diagrammatic level. Basically, you're going to have two types of vertices. You'll have a bracket vertices and a co-bracket vertices. And really you mod out by having more than 2 or more than 3 co-bracket vertices in a diagram. So that story must exist, but Pavel and Benjamin never wrote it up. Next. Likewise, there should be a Chern-Simons theory with gauge group G epsilon. And, well, of course there is, because G epsilon is a metrized Lie algebra, so of course Chern-Simons theory exists. But really, the fact that there is a separation between the upper Borel and the lower Borel means that there are more gauge fixing conditions that you can conceivably write. And the question is there a gauge that leads to a ciphered formula for theta? This is just amusing. I mean, so this inserting epsilon, what does it do to representation theory? I have no idea. I have no clue. This is just complete musing. Okay? Well, there is study theta for links. Does it make sense even if the matrix is not invertible? Does it depend on the choice of which component you have to cut open? Then there is extend theta to rational homology spheres or integer homology sphere. Is there a surgery formula for theta? So if you have theta extended to link, you'd expect that there would be a surgery formula. Is there? And then extend theta to tangles and figure out how it behaves on strand doubling. If I'd had more time, I'd tell you why it's fun. Maybe the whole approach is wrong, and the right thing to do is to understand Kricker and Ohtsuki better and make them more computable. So if Kricker was here, I would have looked at him, but he canceled, I believe, in the last minute. And then there is an expectation that there will be a multivariable version of theta for links, like there is a multivariable Alexander for links, so do it. And task number 27 is why I'm here. Okay, so we're really dreaming that there is a ribbon condition for theta, and there are reasons to dream it, basically because ribbon conditions for the Alexander polynomial come from special types of ciphered surfaces, and if you have a special type of ciphered surface and a ciphered formula, then there might be a special formula for theta, which might lead to a ribbon condition. So that's really my big dream. And finally, there is a bonus task, which I was hoping that Chovanov would be here. So, every talk, there was somebody who ended every talk with, Carthago must be destroyed. And in a similar way, every time you have a knot invariant, you can say, and it must be categorified. So that's the bonus question. And I'll stop here, and oh my God, truly thank you for bearing with me and being here, and for Juji and Eva and Anton for organizing this. And sorry for being such a painful guy.
Additional questions for George?
You mentioned in some question that you need to know about the strand doubling and of theta invariance.
Yeah.
I'm just curious, what about the strand elimination?
That's the same. Strand doubling is really replacing a strand by k copies of itself, and if you set k to be 0, that's strand elimination. So the more general perspective, that's the same. But yes, I agree with you. That's also a question. Where was it? Yes.
So do you expect an interpretation like a kind of non-commutative Riemann-Master torsion, which will solve one of the tasks? For instance, task number 2 on task number 3.
I'm not sure I know what you mean. But if you put meaning into what you said, then the answer would be yes.
For instance, the fact that you invert the presentation matrix reminds me of the computation of Riemann-Master torsions. When you compute the Riemann-Master torsion of a chain complex, you sometimes have to inverse.
That remains I have nothing wise to say. Maybe Roland has, but he's the next speaker, so. Yes?
So the Alexander polynomial has a nice different variable, namely the Conway variables, that make the palindromic things obvious. Did you have any thoughts about those?
I mean, you know we did, right?
It's not in the homework, so.
Yeah, there are a few things I failed to put in the homework. Sorry. Yes, you're right. I mean, are there Conway variables? There's the conjecture, well, yes, you're right. I missed a few homework questions.
No more questions, then let's thank Dror again. And our next speaker is Roland, and his talk will start in 5 minutes, so if anybody needs bathroom or stretch